Hello, everybody, and welcome to session 26 on visual rendering. It's a great pleasure for me to be the chair of this session. My name is Gabriel Sackmann. I'm a professor for computer graphics and virtual reality with the University of Bremen in Germany. Okay, so the first paper is eye dominance guided foveated rendering. It's a paper by Xiaozhu Meng, Rufei Du, and Amitabh Varshney. And Xiao Sheng will give the presentation. She's a PhD candidate in computer science at the University of Maryland, and her advisor is Amitabh Varshney. Her personal interests are foveated rendering and light field rendering. So without further ado, Xiaoshu, please, the Zoom is yours.
Okay, thank you, Gabriel. Morning. Today I'm going to present eye dominance guided foveated rendering. Before we start with this paper, let's play a game together. So firstly, please extend your arms in front of you and create a triangle with your thumbs and index fingers. And next, please frame a distant object within this triangle and keep your both eyes open. You can put the triangle far from you. And step 3, please close your right eye with your left eye open. And step 4, please close your left eye with your right eye open. You may find that the framed object disappears in step 3 or step 4, but remains centered in the other step. It seems that the two eyes are not working together to see the world. Your visual system is showing tendency to prefer seeing perception from one eye over the other. It is somewhat analogous to the right or left-handedness. This phenomenon is called eye dominance or ocular dominance. The preferred eye is called the dominant eye. There has been lots of research exploring the difference between the dominant eye and the non-dominant eye. It has been seen that the dominant eye is better in red-green color discrimination, has shorter reaction time, and has better visual acuity and contrast sensitivity. Now let's get back to VR. The rendering burden for VR is enormous. That's why people come up with the idea of foveated rendering. So here I need to introduce the concept of fovea. Fovea is the center of the human retina, which corresponds to the center of the vision field. The number of visual cells decreases continuously from the center to the periphery. As a result, the resolution of human eyes is highest in the fovea and gradually decreases with the increase of eccentricity. According to a research in 2017, only 4% of the VR pixels belong to the fovea pixels. For the remaining 96%, we are not directly looking at them. So if we can tell the renderer where the user is looking at, and we just let the GPU render the peripheral region with lower quality, the user of the VR headset may not be able to notice that. This is called foveated rendering. As we know, there is always a trade-off between the rendering quality and the frame rate. If we render the peripheral region with lower quality, we can save the cost of rendering and get higher frame rates. So can we do better than just the foveated rendering? Because we know the non-dominant eye has weaker visual acuity and contrast sensitivity. why not render the non-dominant eye with more foliation? Therefore, we started to investigate an eye dominance guided foliated rendering system. Our idea is to use two foliated renderers. For the dominant eye, we render with less foliation, and for the dominant eye, we render with more foliation. So we need a foliation model which allows us to parameterize and change the level of foliation. We use the kernel foliation model, which parameterize the level of foliation with one parameter. In the first pass, we compute the kernel log polar transformation of the G buffer and render to a reduced resolution buffer. In the second pass, we carry out the inverse log polar transformation and perform anti-aliasing to map the reduced resolution buffer to the full resolution screen. We know that the rendering cost is proportional to the rendering resolution because the rendering happens in the reduced resolution buffer now instead of the screen. The shading cost can be greatly reduced. We define the ratio between the width of the screen and the width of the buffer as parameter sigma, and we define the time to render a regular frame as t. So the time to render a kernel foliated frame is t over sigma square. With the increase of parameter sigma, the buffer size will become smaller, and as a result, the rendering quality for the periphery gets lower, but we will get higher and higher speed. Here are some examples with the increase of parameter sigma. Okay, so here is the overview of the eye dominance guided foliation system. Our system uses two foliated renderers with different values for dominant eye and the non-dominant eye. For the dominant eye, we choose a foliation parameter sigma d, which results in an acceptable foliation level for both eyes. And for the non-dominant eye, we choose sigma nd greater than sigma d, which corresponds to a higher foliation level. Because the non-dominant eye is weaker in sensitivity and acuity, the user is unable to notice the difference between the dominant eye and the non-dominant eye. So now we can have a foliated rendering system with adjustable foliation parameters. Our next step is to find the parameters sigma d and sigma nd by conducting a user study. Before we start the user study, we need to find the dominant eye for the participants. We conduct the mouse test, which is exactly the game we have played together. And next, we can conduct the main study in 3 steps. In the first step, the participants estimate the uniform foliation parameter sigma uf, which is acceptable for both eyes. And in the second step, the participant estimates the non-dominant eye foliation parameter sigma nf, which results in the same overall perception as uniform foliation. And in step 3, we conduct a quality evaluation. The user will evaluate the quality of our eye dominance guided foliated rendering with other renderings, such as the regular rendering and traditional foliated rendering. We selected 10 computer-generated environments as the scenes for the user study, and we choose 3 scenes for step 1 and step 2, and we use all the 10 scenes for step 3, the quality evaluation. In our main study, we conduct a slider test and a random test. The 2 tests measure the foliation parameters with different experiment setups. Of course, we expect that the parameters estimated from different tests can coincide. Every test is repeated 3 times for each participant to reduce the inaccuracy in parameter estimation. In step 1, the estimation of sigma UF, the parameter sigma ranges between 1.2 to 3.0. And in step 2, we want to find a parameter which is greater than sigma UF in step 1. So the minimum is sigma UF in step 1, and the maximum is 4.0. We are using a higher upper bound here. Okay, let's take a look at the procedure of the U-slider test. In step 1, we allow the participants to adjust the level of foveation by themselves. He or she can also switch between the full resolution reference and the foveated frame back and forth until he can identify the lowest foveation sigma UF. And in step 2, we present the participants the foveated rendering with sigma UF for the dominant eye, and we allow the user to adjust the level of foveation for the non-dominant eye until he or she finds the highest foveation level, sigma NF, which is perceptually equivalent to the result in step 1. And now we have both sigma UF and sigma NF. We can conduct a quality evaluation by comparing the EFR and other renderings, and the participant will score the difference between the two renderings from score equals 5 to score equals 1. If the score is high, EFR and other renderings will be perceptually similar. And the next is the random test. The random test is very similar to the slider test. The only difference is that the user cannot adjust the level of foveation by themselves. Instead, we show them the foveated rendering with parameter X selected from a shuffled parameter array. And the participant will score the difference between the regular rendering and the foveated rendering. And we choose the maximum X, which results in score equals 5 or score equals 5 as our sigma UF. And in step 2, we estimate sigma NF. We render the frame sigma UF for the dominant eye, and we render the frame with randomly selected parameter for the non-dominant eye, and the user will score the imbalance between the dominant eye and the non-dominant eye. And the quality evaluation is the same as the quality evaluation step in the slider test. We did our user study for 11 users, and now we present the results. We compare sigma UF and sigma NF estimated from 2 tests of the 11 users. We can observe an obvious gap between sigma UF and sigma NF. A paired t-test shows that there is no significant difference between the result of the slider test and the random test. And we can observe that the sigma UF is significantly higher than sigma UF. So the EFR can surely render with higher speed, but what about the perceptual quality of our EFR algorithm? We calculated the percentage of each score in the quality evaluation. We can notice that in the slider test, more than 85% of the users gave a score of 4 or 5, and in the random test, more than 95% of the users gave a score of 4 or 5. So our quality is acceptable. And what about the rendering acceleration? We measure the rendering acceleration with a GTX 1080 for the full headset with a resolution of 1280 by 1440 per eye. And here is a result for the 11 users. We show the frame rate of regular rendering, kernel foveated rendering, and our eye dominance foveated rendering, and we compared the speed up. The speed up of the eye dominance guided foveated rendering compared with the original kernel foveated rendering ranges between 1.06 times to 1.47 times, with an average speed up of 1.35 times. And the speed up of the EFR compared with regular rendering ranges between 2.19 times to 2.71 times, with an average speed up of 2.38 times. And now let's talk about the limitations. One of our challenges is in the foveated rendering is handling artifacts due to temporal aliasing of moving objects. Since our eye dominance guided foveated rendering relies on different levels of foveation for the two eyes, such challenges are likely to be greater. We plan to study and address these challenges in the future work. And the second limitation is that the application must be personalized. And thirdly, we plan to explore how the foveated rendering system can be integrated with the Cyclopean eye to further improve the video experience. And finally, to summarize, firstly, we designed the eye dominance guided foveated rendering, which provides similar visual results as the original foveated rendering and with higher frame rate. And secondly, we conduct user studies to identify the parameters for the dominant eye and the non-dominant eye. And finally, we implemented the eye dominance guided foveation system on the GPU, and it achieves average speed up of 1.35 times. And I will end my talk by showing a demo. So here is our gaze point, which is so you can see it moving. The left one is a non-dominant eye rendered with foveation parameter 3.0, and the right one is a dominant eye rendered with foveation parameter of 2.0. So the foveation level is greater for the non-dominant eye. Thank you. I will be happy to answer your questions.
Okay, thank you very much, Xiaoxu, for your great talk. Just to remind the audience, please ask your questions on Slido, and we actually have 2 questions here.
Mm-hmm.
So actually we have more. One question is, could the dominant eye be recognized automatically? Can you comment on that, or is it necessarily, does it have to be done manually?
I guess it has to be done manually, but I think you only need to do it once, and in the following application, you don't need to detect it anymore.
Mm-hmm. Okay. Another question is that you showed this. You showed the performance, and it seems like the frame rate is around 20 frames per second. Is that correct?
The original frame. Let me see. Because the frame rate is related to the choice of scene and the choice of rendering. So if we just look at the frame rate, it doesn't make much sense. we care more about the speed up, and we want to, yeah.
Okay, so when you use this powerful GPU, the speed up was still around 1.5 or 2, depending on the comparison.
The speed up, yes, the speed up, the maximum speed up we have detected is 1.47 times, but we get this speed up with no sacrifice of perceptual quality. So, for example, the foveated rendering, we sacrifice the peripheral resolution, but for the iDominance guided rendering, we didn't make any sacrifice. We just get more speed up.
Okay, thank you. Just a very quick question. Maybe you can answer it very quickly. Otherwise, we would be running out of time. Question is, what about the temporal artifacts? Can you comment on those? How noticeable are those artifacts?
I guess they will be very, they will be, yes, it will be noticeable. Actually, all the foveated rendering systems suffer with this problem. In my video, I didn't try to solve this. In my video, I didn't solve this problem, but we can solve it by temporal anti-aliasing, and perhaps some other methods such as contrast preservation. Yeah.
Okay. I think we have to leave it at this. Otherwise, we would be running out of time. So thank you again very much, Xiaoshu, for your talk and for the interesting discussions. Okay, so our next talk is, we'll be presenting the paper Accelerated Stereo Rendering with Hybrid Reprojection-Based Rasterization and Adaptive Ray Tracing. The paper is by Nico Wissmann, Martin Misiak, and Arnulf Fuhrmann. All three are with the University of Applied Sciences in Köln. The talk will be given by Martin Misiak. He's a PhD student at the University of Applied Sciences in Köln and also at the University of Würzburg in Germany. His supervisor is Marc-Erich Latuschek. So, Martin, the Zoom is yours.
All right, thank you for the introduction. So hi, my name is Martin Misjak, and on the behalf of my co-authors Nico Wissmann, Arnold Fuhrmann, and Mark-Erich Latoschik, I'll be presenting our work on accelerating stereoscopic rendering. If we look at the requirements for classical desktop rendering and rendering for VR, there are a number of differences between these two systems. For VR, we need to synthesize a stereoscopic image pair. Our displays also span a much larger field of view when compared to desktop monitors. As a result, we have to render more of the scene at a much higher resolution if we wish to maintain the same pixel density. And of course, since we are substituting our entire field of view with an artificial visual stimuli, VR rendering requires a much higher and more stable frame rate. If we combine all of these factors together, we arrive at a large performance gap that currently exists between these two systems. Luckily, research is being done by both academia and industry to address this issue. One way of achieving a high frame rate is to exploit the constraints on human spatial temporal vision, as in the work of Dennis et al. Existing temporal coherences between consecutive frames can also be leveraged to synthesize new in-between frames. Such techniques are already being used by the industry. An example would be the asynchronous space warp by Oculus or motions moving by SteamVR. Foveated rendering, as we just heard, is a very active research area, with the recent research focusing on efficient implementations of multi-resolution rendering and reducing perceptual artifacts in the periphery. Orthogonal to these approaches, VR rendering can also be accelerated by efficiently generating stereoscopic images, as much of the information present in one eye can be reused by the other. Didick et al. Presented an adaptive grid warping approach for quickly synthesizing the second eye image. Reprojection errors are filled in by simple inpainting and by sampling from previous frames. Schollmeier et al. Improve upon Didick's approach by introducing a more sophisticated inpainting technique and a new heuristic for grid subdivision. They also support the reprojection of semi-transparent materials. Our presented approach also aims at accelerating stereoscopic rendering. We share some core similarities to the work of Didick and Schollmeier, as we also employ an adaptive grid warping approach. However, we differ in a few aspects, the most notable being the handling of reprojection errors caused by disocclusions. To this end, we make use of hardware-accelerated adaptive ray tracing available on the latest GPUs, and we correctly reconstruct the missing information, a feat not achievable with common inpainting techniques. Adaptive ray tracing has been used to reconstruct reprojection errors before. In the work of Adelson and Hodges, in the context of synthesizing animated frames in fully ray-traced environments, and by Vaya et al., who implemented a ray-traced foveated rendering system. So let's take a look at our rendering system's architecture. We start off by rendering the left eye image as usual using a standard deferred pipeline. Prior to submitting our finished image to the left portion of our output display, we perform a tone mapping pass. And that's basically it for the left eye. Now onto the generation of the right eye image. To this end, the left eye image as computed by the lighting stage, as well as its associated depth buffer, are forwarded to the reprojection pass. Here, the radiance information from the left eye is reprojected into the right view using an adaptive grid warping approach. The reprojection will contain errors caused by areas previously not visible in the left eye. We detect these regions and discard the associated pixels from the output image. The resulting holes are then filled with correct information in a subsequent ray tracing pass. And finally, the finished reprojected image is tone mapped and submitted to the right portion of the output display. It should be noted that our reprojection algorithm does not depend on any specific rendering pipeline, and the reprojection can also be made from right to left. All right, so in the following, we'll take a closer look at the reprojection and hole filling passes, as these are the more interesting ones. So first off, let me briefly explain how grid warping works as a reprojection mechanism, since it's already been mentioned a few times in my talk. Let's assume we have the color and depth information from viewpoint A, which is in our use case the left eye. We use this information to displace a grid of n times n vertices and map the color texture onto the surface of our grid. The grid mesh is then simply rasterized from another viewpoint, our right eye, and we obtain our reprojected image. Now, obviously, the reprojection quality is primarily dependent on the grid's resolution. Ideally, we would like to use the grid with the same resolution as our input image. So for an HD image, this would be 2 million vertices and 8 million vertices for an 4K image. However, such a high number of vertices can itself become a limiting factor, and practically it's not even necessary, as many vertices can be warped together. Therefore, it's a better idea to rather subdivide a grid adaptively based on the underlying in-depth information. However, the question now becomes, how do we decide which grid cell needs to be subdivided and which not? Which brings us to our first step in our reprojection path, compute subdivision heuristic. Didek et al. Subdivide a grid cell if the difference between the maximum and minimum depth values inside cross a certain threshold. Schollmeier et al. Employ a collinearity measure where a cell is subdivided based on the curvature formed by its depth values. Both of these approaches operate solely on the depth values and don't consider the limitations of the human visual system. Our approach, on the other hand, is specifically aimed at stereoscopic rendering, as it is based on binacular parallax and evaluates depth discontinuities in relation to the distance at which they occur. Let's take a quick detour to binacular parallax. If our eyes converge onto a point, they rotate inwards and their lines of sight cross at that specific point. The angle which is formed by the crossing lines of sight is referred to as binacular parallax. It's dependent on the interpupillary distance and the distance of the convergence point. Binacular parallax plays a significant role in depth discrimination based on stereoscopic vision. So let's say we want to differentiate between the depths of 2 points, A and B. For this, we have to consider the binacular parallax of converging on both points. If the difference between the angles alpha and beta is above a certain threshold, let's call it delta, we can discriminate between these two depths based on stereoscopic vision alone. The threshold value delta is referred also as stereoequity, and for a major part of the population is in the range between 0.5 and 1 minutes of arc. The rationale behind our subdivision heuristic is basically, if a grid cell contains depth values which are not discriminable by our stereoscopic vision, we don't have to subdivide the cell, as its reprojection will result in the same perceived depth information an unsubdivided cell would deliver. Detailed information about our heuristics implementation can be found in our paper. So let's see this subdivision heuristic in action. On the left, we can see a visualization of the user's position as he moves through the scene. On the right, the user's viewport is shown and a wireframe rendering of the subdivided grid. We can observe that grid cells, which were previously not subdivided, for example, the area around the door frame, become subdivided as the user moves closer, increasing the binacular parallax difference. Right, so once the grid cells are marked, the subdivision can take place. We implemented this step with the help of the hardware tessellator, as it offers superior performance in comparison to a geometry shader. Each marked grid cell is tessellated only once and with a factor of 16. When applied to our starting grid resolution of 16 by 16 pixels, this results in a one-to-one mapping. With the correct subdivision, the grid can then be reprojected into the viewport of the right eye with the mechanism described earlier. One prominent artifact of grid reprojections are so-called rubber sheet artifacts, which wrongly connect surfaces at depth discontinuities. They can cover regions which were previously not visible in the left eye, as well as occlude regions where correct information was available. Therefore, our next step in the pipeline is to detect these regions and discard the affected fragments. Details can be found in the paper on this. The resulting holes in the reprojected image now need to be filled. This happens in our next and final stage. One simple way of solving this problem is by choosing the color of a random neighboring fragment. While very efficient, this method is only suitable for filling in very small regions. Schollmeier et al. Implemented a more sophisticated inpainting technique. However, a core limitation still remains. No previously hidden information can be generated this way. So instead of hiding the reprojection errors, we chose to correctly reconstruct them. To this end, we use an adaptive ray tracing approach implemented using the new DirectX ray tracing API. On supported GPUs, the acceleration structure traversal and the triangle intersection tests can be performed on dedicated hardware and in parallel to rasterization. Implementation-wise, 3 new shaders are required: array generation, closest hit, and a miss shader. The ray generation shader dispatches primary visibility rays for fragments which have been discarded in the previous step. The hit shader executes the same shading code as a lighting pass for the left eye, while the miss shader simply samples a background color. Unlike in rasterization, a single ray cannot compute the gradient of the texture coordinates at a specific point. Therefore, we resolve to a cone footprint approximation for selecting the MIP level during ray tracing. Here we can see the difference between the texture MIP levels between regular rasterization and our cone footprint approximation. In addition to the ray tracing approach, we also implemented a second hole filling method based on regular rasterization. The missing fragments are reconstructed by simply re-rendering the seed from the right eye's perspective. To achieve a speed up over naive stereo rendering, the fragment shader is only evaluated for the discarded regions. We did this as we wanted to compare the hole filling performance of our dedicated ray tracing hardware against the GPU's own rasterizer. Okay, so let's take a look at our evaluation of our algorithm. We did our benchmark of 4 popular test scenes. We chose them as their complexity regarding geometry, textures, and lighting is somewhere in the ballpark of modern computer games. Our test hardware consists of a modern CPU and a powerful recent GPU with ray tracing acceleration. For the benchmark itself, we measured the total time it takes to render 1000 frames on a predetermined camera path. We benchmarked all scenes in 2 resolutions, Full HD and 4K. Our 3 test systems were Plain Stereo, which is our reference system, Repro ReRaster, our reprojection algorithm with the rasterization-based hole filling, and Repro RT, which is our reprojection algorithm with the ray-traced hole filling. The total time encompasses the costs of rendering the left eye and the reprojection step. The 2 main results are the following. Reprojection is almost always faster than naive stereo rendering, the only exception being the bistro exterior and night scenes in HD, where the re-raster system actually performed worse than the naive stereo rendering. The second finding, the Repro ray tracing system outperformed the re-raster system in all instances, achieving speedups ranging from 28 to 55%. Here is a breakdown of the individual render stages of both reprojection scenes in the bistro interior scene. The first 2 passes belong to the left eye, followed by the reprojection stages, which are performed under 1 millisecond for HD and under 2 milliseconds for 4K resolutions. The following figure shows the hole filling performance of both systems in more detail. Ray traced hole filling clearly outperforms the re-raster system and is on average 0.15 milliseconds faster in HD and even 0.5 milliseconds for 4K. The differences are even larger for the other scenes, as bistro interior could be considered a worst case scenario with many simultaneous disocclusions. So in conclusion, we presented a hybrid reprojection-based rendering system to accelerate stereoscopic rendering. We achieve a significant speedup over naive stereo rendering while correctly reconstructing disoccluded regions. Our system leverages modern hardware-accelerated ray tracing and can be easily implemented into an existing pipeline. In terms of limitations, we are currently reprojecting only opaque diffuse surfaces. While specular materials can be reprojected, their stereoscopic highlight disparity is not preserved. For future work, we would like to test our system's performance in animated scenes. We're quite optimistic in this regard, as the DirectX ray tracing API, which is responsible for the BVH updates, is targeted towards highly interactive applications. And in addition, we would also like to evaluate our system's quality on a perceptual level. So thank you for your attention, and keep an eye out on our publications page, as we are planning to release the source code of our project shortly.
Okay, thank you very much, Martin, for your great talk. We'll do the Q&A right away. And there are some questions on Slido. One question is, did you compare your solution to other state-of-the-art accelerated stereo techniques like single pass stereo, multi-view rendering, and so on?
We did not. However, these techniques, basically they aim at an acceleration of the CPU performance, right? So they are designed to reduce CPU costs for submitting additional draw costs for the second eye. And what we do is basically we also have more performance for the GPU side, since we don't shade as many pixels.
Okay, thank you. Another question asks about some prior work by Smith et al., a shared scene graph image warping architecture for VR. Maybe you are aware of that.
I have to confess, that not really. Okay. So
okay,
I'll have to look that one up.
Okay, it was published in 2010. Okay. So another question is, how big is the difference? Did you measure the difference of the images that you generate with your approach versus the, brute force rendering from scratch?
So there are, of course, some differences, because the main difference is basically the MIP level in which we sample our textures, because it's different for ray tracing and for rasterization. So if we would put these two images in a structural similarity index, we would get, of course, different values. However, on a perceptual level, at least for us as developers, we didn't see much difference between brute force rasterization and our technique. However, we definitely need to do a perceptual evaluation with multiple users. That's also our future work.
Okay, thank you very much. I think we have to leave it here in the interest of time. Thanks a lot again, Martin, for your talk and the Q&A. And while we transition to the next talk, we will make a quick break. And for those in hubs, for those attending the session in hubs, you might want to say hi to your fellow neighbor while we switch to the next talk.
Hello everyone, my name is Ryan Beams and I'm from the Food and Drug Administration. I'm going to be talking to you today about some work we've been doing on the angular dependence of spatial resolution in virtual reality displays. And this work was done with Brandon Collins, Andrea Kim, and Aldo Badano. First, just a disclaimer of the mention of any commercial products during this presentation. So a common question I get from people when I mention that I'm at the FDA and we're doing research on augmented and virtual reality is, why is the FDA interested in working in this space? And one way you can think about that is considering the wide range of applications that exist for AR and VR devices. The most obvious, of course, being entertainment, but it's also being used extensively for training, education, teleconferencing, remote control, and another interesting one is data visualization. And you can think about how you can take any of these applications and translate them into the medical profession. Or instead, we're looking at training and simulations, education. Telemedicine is an interesting one where you could have medical professionals in remote locations interacting with each other, potentially with patients, and with the same medical data. Remote surgery is also another exciting application for these technologies. And then data visualization as well, because you can take these already three-dimensional medical images and then open up new possibilities for how doctors can interact with them to understand them in a more intuitive way. And this is being explored for diagnostics and surgery planning. And then finally, entertainment can actually be translated almost directly for applications such as pain management and other therapeutic applications. So because of the wide range in medical applications, and all of these have their own challenges to them, we recently hosted a public workshop, and the goal of this public workshop was to get the stakeholders from all the different arenas, so academics, government, medical professionals, industry, both on the device development and on the application development, into one location to discuss what are the challenges in using these technologies for virtual and augmented reality. And this entire workshop will be available to the public, so if you missed it and you'd like to listen to it, I invite you to do that once the link is live. And as a part of that, we also had some very nice panel discussions about what are the methods and ways to go forward with this effort. Within the FDA, in the science and engineering laboratories, we have a medical extended reality research program. And as a part of this program, we are looking at a number of different topics, including color rendering and understanding how the pipeline impacts an input medical image compared to what the final user sees. Also characterizing the optical performance, such as the eye box and how you mount the headset on your head, chromatic aberrations, contrast, and then resolution, which I'll spend my time talking about during this presentation. And then finally, at the end, these devices have to go onto the user. And so we're also looking at human factors issues such as motion tracking in AR surgery. Okay, so now to get kind of to the important point of this presentation, I want to talk about the resolution dependence across the field of view. So if we think about starting with some initial image, in this case I've taken digital pathology as an example. This could be surgery planning, could be a wide range of images. And if we have this image on a conventional display, the resolution, regardless of where you look on the image, is going to be fairly consistent. So if we look in the center versus over on the right side, resolution still looks good and as you would expect. That's not necessarily the case when you move to a head-mounted display, however, because there's additional optics that are in there as well that can impact the contrast, color performance, resolution, among other things. So if we look at this same patch on the head-mounted display, you notice the resolution's actually dropped off quite significantly. We've also looked at this in terms of contrast. So if we start with looking over a 30-degree field of view of the head-mounted display and look at the percent contrast, as you start to go to higher resolution features, the contrast starts to drop off fairly quickly. And so it really illustrates that where you are in the field of view and the frequencies, the spatial frequencies of the content, impacts the final result. Okay, so now that we agree that where you are in the field of view is important, we should probably go about measuring that. Well, what would be the best way to do that? So if we think about this simple cartoon of how a human looking at this head-mounted display, and they have some field of view for each eye. So we could just replace the eye with a camera, and this would be great because it's a fast measurement, single measurement, it's easy. But one problem is it's not how the eye works, because the camera system has a fairly consistent resolution over the entire field of view, whereas the eye does not. So this is looking at the distribution of rods and cones across the eye. And of course, the eye has a fairly narrow region called the fovea that has high resolution. And to make a two-dimensional image, the eye scans across it. So an alternative way to take these measurements is to do an angle scanning approach that more closely mimics the human eye. But it comes, of course, at the cost of being slower and requiring scan stages. Now, even if we agree at this point that we should do an angle scanning method because that more closely agrees with the human eye, the problem is still not solved. And this has been a discussion topic in IEC about even if you're going to do a rotation, what's the point at which you rotate? So the two different approaches are an eye rotation versus a pupil rotation. The eye rotation is what we biologically do, where we have a center point and the eye moves up and down. One thing to note is as the eye does that, the pupil moves off of this optical axis. Whereas if you do a pupil rotation, you keep the pupil fixed on the optical axis, but the eye is actually rotating out of its socket. And while this may seem like a small difference, there's a recent paper by John Pensick exploring these differences in the case of distortion. What you actually see is the pupil rotation in red versus eye rotation in green. You actually get fairly different results. And so this really illustrates that if you go about measuring some of the properties of these head-mounted displays, you have to think very carefully about how you go about measuring. Okay, so the focus of this talk, though, is resolution, and we also need to think about how we measure that. Now, a common approach for measuring camera systems is to do a slanted edge test. But this is actually kind of difficult for displays, and particularly head-mounted displays, because there's a subpixel pattern. So our slanted edge is going to cut across those subpixels, and then the profile of that edge is suddenly going to become quite complicated. Alternative method that we decided to use is look at the line spread response, where we have turned on a single line of pixels, and then you can measure the width of that, and then use that to determine what the resolution is of your system. In the laboratory, the way this looks is we have a imaging system with a CMOS sensor, a lens in front, and then we put the pupil out in front of the lens to more closely mimic the human eye. And then in the wide field case, the pupil's fixed, we just image it onto the sensor. In the angle scanning method, however, we're rotating the pupil of the camera, and so the bundle of arrays that we're collecting and mapping onto that CMOS sensor is different, and that's going to impact the final measurement and final image that we get out of the system. The way this looks in the lab is we have our head-mounted display with a camera on an XYZ theta stage. It's fairly straightforward. Okay, so if we then set this up, go in the lab, start taking measurements, and we start in the center of the field of view with our line spread response. We want to look at this single white line of pixels. You can nicely see the subpixel pattern. You can shown here in the zoom in. And then to maybe get a little bit better feel for what's going on, you can also look at just, say, the green subpixels, and we get a really nice symmetric shape out, which is what we would hope for. However, if we go off the center of the field of view to say plus minus 10 degrees, for both the eye rotation case and the wide field case, we start to have a fairly large decrease in resolution. We get this separation of the colors and this kind of rainbowing effect. And if we look at just the green subpixels, you get this kind of comet shape. And it's more significant for the eye rotation case than the wide field. And the reason this happens is due to the aberrations of the lens. And so one example of that is the chromatic aberration, but there's other ones that are also coming into play here to impact what the final image that you get out as you go across the field of view. So then to make this a little more quantitative, we can perform these line spread response measurements across the field of view of the display. And so in this case, we're just looking from -15 to +15 degrees. That's along the horizontal axis. And then the line spread response is along the vertical. And so what we find is that in the center, the resolution is the best, and then it starts to decrease as you go away from the center of the field of view. And that's the case for both the eye rotation and the wide field case. And then you can look at the line spread response profiles, and again, you see as you go off axis, it starts to decrease in signal strength and the width gets wider. So one thing we decided to do with this was to compare how the Vive and Vive Pro looked for these same measurements. And the reason for doing that is the design is quite similar, but one has more pixels than the other. So it allows you to ask the question, how much does it really help you to add more pixels to the display? And what we see is that we get similar kind of effects with this fanning of the resolution. And then in the center, the resolution is in fact better, but it doesn't necessarily help you too much as you go off axis. Another way to consider how the resolution is changing is we can do the change the line spread response into the modulation transfer function, and you can think about the modulation transfer function as being the filter function for the optical system. So if we start with our impulse response or line that we send in, we get some line spread response out. We take the Fourier transform of that to get the modulation transfer function where it's spatial frequency versus percent contrast. For a lower resolution system, we have a wider line spread response, and then the modulation transfer function drops off faster, meaning that the cutoff frequency is lower. Another thing we can do with this is we can look at the 50% contrast point and what spatial frequency that corresponds to. So for the Vive and Vive Pro, using the two different methods, these are the results for the modulation transfer function. You can see the Vive Pro has a higher spatial frequency cutoff than the Vive, which you would expect, and the eye rotation drops off faster than the wide field method. And as a reference, here's the modulation transfer function of our camera system. So as I mentioned on the previous slide, you can also take all this data and kind of compress it down by looking at the 50% contrast level. So that's what we've done here. So this is the spatial frequency at where the MTF equals 0.5. Along the horizontal is the angle in the field of view. The red lines show the Vive Pro and the blue shows the Vive. And so what you see in the center is that the Vive Pro has higher resolution than the Vive, which you would expect, but then as you go off axis by say 5-10 degrees, the performance of the two is actually quite similar. And then also importantly, the measurement method for the angle scanning drops off faster than the wide field approach. And then finally, the way we can compare these is look at the full width half max of the line spread response as a function of the angle in the field of view. And again, we see that we have this kind of narrow 10-degree window where the device performs quite well, and then it starts to drop off quite quickly in resolution, and it drops off much faster for the angle scanning method. And if you look at the percent difference between the two methods, it's say 15 degrees, it's around a 40% difference between the two methods. And this really illustrates that it's important to consider how you're going about measuring these devices. So with that, I would like to conclude. I've shown that the measurement method is very important to consider and can greatly affect the results. The wide field method tends to overestimate the resolution of the head-mounted display. And then finally, across the field of view, the optical performance and not the display limits the resolution, which is an important consideration for the rendering pipeline, as well as for applications where consistent image quality across the field of view is important, such as surgery planning or diagnostics. Finally, in future work, we're interested in applying this method to other subpixel patterns, as well as extending it to binocular measurements. So with that, I would like to thank you for your attention.
Okay, thank you very much, Ryan, for your great talk. I have a question for you regarding the measurement. The retina of the human eye is basically a curved imaging surface, right? So would that have an effect on the results, or would that change the acuity? Can you comment on that?
Yeah, so that's a great question. We actually got a lot of really good feedback in the review cycle. So for the reviewers, I'd like to thank them. This is one of the questions that we received. So there's a couple of things. So I think it would potentially change the results a bit. The reason we went with a flat detector was a couple-fold. One, that's what's commercially available, and part of what we're trying to work towards is provide guidances for how companies can do these measurements. So keeping it towards camera systems that are easier to buy makes sense. As far as the curved, how it would change things, yeah, so that's a good question. I think it's something we need to look into more going forward. But yeah, it's certainly a very good question to try to push it to be more like the human eye.
Okay, thank you. Another question is, are there any implications on the design of head-mounted displays from your research, or can you, are there any recommendations coming out of your research for future head-mounted displays? Should they be built differently?
So one thing that we learned from this is that, as we showed, that the Vive and Vive Pro, despite having fairly different numbers of pixels, the performance wasn't too different. So the main takeaway message that we got from that is, in order to push these headsets to be closer to the resolution of the eye, I think the optical performance needs to be improved in the lens design. I think this is well known by manufacturers, but to make a thin, lightweight lens that has this level of performance over the field of view is an extremely difficult optics problem. One thing we're also interested in doing going forward is there's been some work at Intel looking at using different types of subpixel patterns and seeing how that affects the resolution. This was all done with the same subpixel pattern, but that would be something else to consider as well and see how that impacts the results.
Okay, thank you very much. So that's the questions I have for you at this point. Thank you very much again, Ryan. And I guess we have a quick transition for the next talk. So stand by.
Hello everyone, my name is Sino Liu. I am a joint PhD student in University of Science and Technology Beijing and Carnegie Mellon University. Today, I will present for the paper Multiple Scale Simulation Method for Liquid with Trapped Air under particle-based framework. So, what are we doing? We are adding air materials to fluid, especially liquid. Exciting fluid simulation method is able to describe the motion of fluid realistically, which puts higher requirements on the detailed simulation. However, the physical description of air materials is extremely complex, which makes it difficult to simulate them realistically. In this video, a dolphin drops into the sea and makes some turbulence. After adding materials such as bubbles and foams, the visual effect is enhanced. The fluid is simulated by a classical particle-based method, SPH method, which is short for smooth particle hydrodynamics. Fluid is composed of thousands of moving fluid particles. They are represented by pink spheres. The air materials are also present by particles and are added to the simulation by a post-processing scheme. In this figure, all particles are represented by white spheres. In terms of generation of air material, it can be divided into three categories according to the mechanism: trapped air, nucleation, and boiling. First, when moving intensely or rushing quickly, air will be trapped in fluid, such as pouring water into a glass. Second, when environment such as temperature and pressure change, air that originally dissolved in water may precipitate to generate nucleation bubbles, like foam in beers. Third, when the liquid is heated above its boiling point, surface and internal fluid particles vaporize simultaneously, like bubbles in hot water. In this paper, we focus on trapped air in liquid. The study of trapped air is mainly divided into two types according to the size of air materials. When modeling the large-size air material, the fluid is usually regarded as air-liquid two-phase fluid, and a complex physical model will be established. This type of model are able to describe the shape change of bubbles vividly, but the calculation process is very time-consuming. Besides, the mass transfer process between air particles is not well described. As for the simulation of small-size air materials, the shape and the size of particles is usually ignored, and only the microscopic motion is described. Generally, this type of model is a post-processing model which can enhance visual effect with negligible computational overhead. Besides, without Brownian motion, large number of air particles will move with similar patterns and result in a periodic distribution. In real life, air bubbles of different sizes are usually generated at the same time. Simulating different scales of air materials simultaneously in a unified framework can achieve a more realistic result. Therefore, we propose a unified multiple-scale air material simulation method for particle-based fluid. For large-size air material, the mass transfer phenomenon is described based on the inverse diffusion equation, and the interaction scheme is improved using a new high-order kernel function. For small-size air material, we improved the velocity update function to get a better result, and the Brownian motion is added to solve the periodic distribution problem. Next, I will illustrate our method in detail. The quantity of air material is generated by each fluid particles is based on the velocity difference and the kinetic energy. With a maximum sampling rate, we can obtain the number of new generated air particles. Next, we draw a cylinder based on the trajectory of the fluid particle and randomly initialize the air particles in this area. Since the cylinder is really small, air particles tend to form a cluster under this scheme. To solve this problem, we set the size of the generation area, the cylinder, to be adjustable, which means it will become more larger. Then, the air particles are divided into 6 steps based on the size and coupling degree with fluid, as shown in Table 1. In physics, bubbles radius in a liquid obeys a log-normal distribution. A random number obeying a log-normal distribution is used to determine the initial radius of air particles. A controllable parameter is introduced as a threshold for dividing the size of the air particles. When the radius is larger than this threshold, the air particles are regarded as large-size air material, while the other will be regarded as small-size air material, and the radius of small-size air particle is valued as E. This is an injecting water experiment with 29,000 fluid particles. A is the real sense. B, C, and D are the simulation result with particle results on the left and the rendered result on the right. In particle result, small-size air material and large-size air material are marked as red dot and blue sphere respectively. By adjusting the control parameter, the occupation of large air particle is changed, and different styles are realized. Both large-size and small-size air particles are classified by the coupling degree with fluid. Subfigure B shows the render result of air materials generated by blocks falling into water. The marked result is shown in subfigure C, where spray particle, foam particle, and bubble particle are marked by light blue, green, and red respectively. Third, air particles are dynamic surviving particles. Small air particles with lower surface energy are more stable. So, in each time step, we randomly remove the air particle based on their age and radius. The probability that an air particle is deleted is controlled by this function. In this paper, two dynamics models are established for different sizes of air material. The small-size air particle move under the gravity, the buoyancy, and the coupling force with fluid, while the large-size air particle will also coupling with neighbor air particles and solid particles. As shown in this figure, in each time step, the velocity of the air is calculated together by the velocity variation caused by the gravity, the buoyancy, and the drag force of the neighboring fluid particle. The value of the coupling parameter depends on the degree of coupling. We also implement Brownian motion. Two neighbor air particles have similar fluid neighbors. The motion of air particle depends to a large extent on the average velocity of its neighboring fluid particles. Therefore, if Brownian motion is not added, regular periodic distribution of air material will be observed. The Schlick function is used to describe the velocity offset angle of each small bubble particles. The probability of air particle to move following the Brownian motion is determined by the degree of choice of this area. This is a tiled water injection experiment with 20,000 particles. In order to see the effect of Brownian motion more clearly, only the small-size air particles are rendered. By adjusting the parameter kappa, the motion freedom degree of air material changes. The value of kappa in subfigure B, C, and D is 1, 0.8, and 0.6, respectively. When kappa equals to 1, Brownian motion is not added, and the distribution of air material is periodic. After adding Brownian motion, the zero effect is improved. The dynamics model of large-size air material is slightly different to small-size air material. Due to the large volume, their coupling degree with rigid body and the neighbor air material is relatively high. Therefore, in addition to the gravity and the coupling force with fluid, the interaction with rigid body and the air material are also need to be described. Air particles that are not in Plateau equilibrium are unstable and will quickly be rearranged under surface tension. The Plateau equilibrium distance of two air particles is shown on the screen, where lambda is set based on the coupling degree. We use a new high-order kernel function to deal with the interaction between two large air particles. The peak value of our function is a finite value, thereby avoiding the explosion phenomenon. We use a pattern similar to air coupling to describe the coupling force between solid particle and air particle, where the control parameter takes the different values. According to Laplace-Young's law, pressure of small particle is larger than that of the larger bubbles. When two bubbles contact each other, the smaller one tends to press internal air into the larger one. Therefore, we describe the process of mass transfer using an inverse diffusion equation. The discretized mass transfer formula is shown on the screen. Besides, only two large bubbles with a relative larger volume difference will transfer air between each other, and the threshold value is 0.8. This is to avoid air transfer between all bubbles, resulting in a rapid reduce of large air materials. Our method tends to generate air particles in fast-moving areas, and the one-way coupling scheme makes it more suitable for efficient real-time simulation rather than high-accuracy simulation. In terms of dilation scheme, although we set the large-size air particle with larger surface energy to be more easier to be dilated, some large-size spray particles still have a long lifetime. These surviving air particles will be able to jump out of the liquid surface, affecting the visual effect of animation. This issue could potentially be resolved by using a smaller buoyancy parameter to reduce the velocity of these particles as they approach the surface. Fully optimization of this problem will be our future research work. We also plan to combine our method with some turbulence simulation method to further enhance the visual effect. This is the end of our presentation. If you have any questions, please feel free to contact us. Thank you very much for your attention.
Okay, thank you, Sinyu, for your presentation. I was wondering if you could comment on the running times.
I didn't mention the running time in the rendering time in my paper because the rendering is really time consuming. But you can see the particle result Yeah.
It seems like
I
the
didn't
audio
mention
is...
that because if you're rendering the result, it's really very time consuming. But the particle-based result is really very fast. It's about just use some 2 or 3 seconds for one frame. Yeah.
Okay, thank you. You also mentioned that you used SPH software, or you integrated your methods into an SPH software. Can you tell which one it is?
The SPH method is short for smooth particle hydrodynamics. It's one of the particle-based methods in fluid simulation. And I also mentioned it in the relative work part. You can find some reference in this part. It's generally simulate all the fluid as some particles, like like all the fluid is simulated by some moving particles, and we need to calculate the velocity of these moving fluid particles, and using that, the fluid is simulating very realistically. Yeah.
Okay, did you use some existing software?
Could you pardon?
Did you use some existing software?
No, it's not a software. We just implement it in ourselves.
Okay, thank you.
Mm-hmm.
Okay, so that's the questions I have for you. Thank you very much again for the QA. And then we will transition to the last paper in this session. So the last but not least paper in this session is Where to Display, How Interface Position Affects Comfort and Task Switching Time on Glanceable Interfaces. The authors are Samad Imamov, Daniel Montzel, and Wallace Lages. All 3 of them are with the Center for Human-Computer Interaction at Virginia Tech. The talk will be given by Wallace Santos Lages. He's an assistant professor at the School of Visual Arts of Virginia Tech. And with that, I would like to hand the Zoom over to you. Wallace, please.
Thank you for a kind introduction, Gabriel. So this paper was conducted by my students last year in my lab. And I would like to acknowledge the support we had from a Google Research Grant. So I will begin by giving an introduction for the work, and then I'm going to describe the study, followed by results and conclusion. So there are many scenarios that involve like AR and VR as a contextual display. For example, if we were in a real-life conference, we could use AR to create virtual badges for each participant, right? Much like we have in hubs. The content in this case is associated with a specific position in space, right? But if there are multiple people around, then your interface needs to be smart enough to arrange the annotations to avoid occlusion, but they're still somewhat bounded to the physical location in space, right? But not all content is tied to a position in space. For example, if we have a calendar or a notification, it can be placed anywhere. One way to think about then is according to the reference frame they are attached to. For example, the calendar may be attached to your head, and as you move, you look around, it moves along with you, or it could be fixed to a relative position in your body, or it could stay fixed in a position in the world. From a visual perspective, it makes a lot of sense to place information in the periphery of the display, because then you can keep the central part of the display clear. And that's why many designs are like this. However, in many cases, don't really want information to be shown all the time, even if it's in the periphery. Another aspect to consider is that once you start paying attention to something, it's really hard to be aware of what is going on in other parts of the display, even if it's right in front of you. So it may change and you won't notice. And since you're distracted in any way, what matters here is reducing the time that you spent away from your main task. In fact, this is the definition that Tara Matthews used in 2006 for a glanceable interface. She defined it as interface that allow you to focus on the primary task, switch to a glanceable display when you need to, and easily continue doing what you're doing before. It's important to note that this is not desired or possible for every content, right? For example, if you're typing a document or playing a game, it requires like focused attention, but it works well with other things we do in our daily lives. For example, checking the calendar or checking out the time or looking at text message that you just received. So what we sought to do with the study is try to answer these questions. So if we can place a glanceable content anywhere in the world, what is the best place for it? We could also like investigate how the performance and comfort changes as we vary these positions. As I mentioned before, there are many studies like comparing reference frames and even positions in a plane. However, we noticed a lack of like a systematic study of these questions. And in particular, we couldn't find any work looking at the effect of distance from the user. And we suspected that shorter distance would reduce the time necessary to change like fixation between the different targets. And it will also facilitate like the shift of attention between them. So formally, our hypothesis was that instead of preferring information in the periphery, users would actually be faster and prefer content displayed in 3D locations closer to the position of the primary task. We expect that efficiency and comfort would also decrease with the distance from the main task. So we designed the study with the goal of examining the effect of position of world-locked interface relative to the point of interest of the primary task. In this study, participants switched between the real world and a glanceable interface. In our case, the task appeared on a TV, and the participant would then use a glanceable interface to gather additional information to complete the task. We conducted an experiment using mixed reality simulation, which is to say, basically we simulated an AR device with a wide field of view inside a virtual reality environment. And we created a detailed room to serve as a realistic background, and then we rendered a glanceable interface with a transparent material on top of it to simulate an AR interface. So this is another view of the experiment scene. The task was displayed in a TV, like 4 meters away from the user, and the interface were placed in various positions between 1 and 3 meters. In our study, our interface were within 56 degrees. Our study used a within subjects design, and we recruited 22 participants. We had 3 independent variables: depth, vertical displacement, and horizontal displacement, using a total of 18 conditions. And each participant did 12 tries per condition. We used an HTC Vive Pro headset and an Xbox controller for input. So let me explain a little bit about the task. So the task consisted in selecting 2 highlighted symbols. The first one appeared in the TV in the beginning of the task. In this case, it was the yellow circle. To obtain the second symbol, the participant then presses a button to call the glanceable interface and then searches for the corresponding symbol in a list. In this case, would be the pink triangle. Once the participant catches that, then it presses the same button again to dismiss the interface and then resumes the task on the TV. And the final step then is to press the buttons corresponding to the first circle, first symbol, and the second symbol. And there are 2 intervals that are important here. The first is the time the participants spend looking away from the glanceable interface after it's activated. This is the time between calling the interface and dismissing it. We call it the glanceable time. And the second one is the time the participants take to get back to the task. This is the time between dismissing the interface and inputting the first symbol. We call it return time. And the sum of the two time indicate how long the participant spent away from the main task. That is the context switching time. We also use the questionnaire and an interview to gather like participant qualitative feedback. So overall, participants were very accurate in these tasks. The mean number of errors was 3.4 out of 216 trials. And this plot shows the position of the errors for each position. The colors here indicate the same participant. So the maximum number of errors was 16 by a single participant. This is one like highlighted in pink. And there was no significant difference between the positions with errors. These are the main switching times and standard deviations for the different vertical and horizontal angles for the frontal view. So the y-axis here is the vertical displacement and the x-axis is the horizontal displacement. So in other words, this is the view from the perspective of the participant. So darker means faster. So the center and lower positions were faster than up and down. This is the same plot, but now from a side view. The y-axis is still vertical displacement, but at the x-axis is now distance. So the lower position closer to the TV was faster, and the higher position closer to the users was the slowest. Now the results from the top view. So the y-axis here is the horizontal displacement, and the x-axis is the distance from the participant. The positions like here in the middle and closer to the TV were faster. So to understand the contribution of the distance and angles in the performance of the participants, we fitted the generalized multiple regression using R. Horizontal angle, vertical angle, and distance were all significant predictors of time. Here we can see how the time changes with distance. So lower means faster. So participants spend less time switching as the distance increases. They're also faster when the interface was centered right in front of them, which is the red line. And here in this other plot, we can see how the vertical angle affected the switching time. The time increases here with the positive vertical angles, right? So upwards. So the participant were faster looking down than looking up, right? Again, here we see that participants were faster with the central positions, right? The red line. So regarding the preferences, these are the weighted average for the 5 best positions in terms of comfort. Participants clearly preferred like the central and lower positions. It was indicated by the blue arrows. And within these two groups, the distance of 2 and 3 meters were better ranked than the closest one, which is the one at 1 meter. So when we asked the participants to choose a single most comfort position, 60% of them preferred screens at 2 meters and 64% preferred screens at eye level. So considering only the 2D plane, our results kind of agree with previous studies on computer screens, which have found that like gaze directions between 10 and 25 degrees downwards are more comfortable at shorter distance. The difference between vertical and horizontal angles was kind of unexpected. So prior literature has given like similar exertion rates for vertical and horizontal angles up to 40 degrees. So it shouldn't really matter if you're looking up, down, left, or right. So we suspected that the HMD weight may have modified like the center of gravity in a way that affected more the lateral movements than the vertical ones. And finally, we also saw a slight disagreement between the participant comfort rating and their performance data. So participants preferred screens at eye level at 2 meters distance, but were faster with screens in lower positions at 3 meters distance. So it would be interesting to see how this preference changed in like a longer study. So summarizing, we found evidence that participants are faster when the content was closer to the TV and away from them. We also saw that completion time and comfort increased with vertical and horizontal displacement. And based on these findings, we would recommend like avoiding placing glanceable content too far away in space from the main task. It's also important to highlight some limitations of this study. So first, we only cover positions between the user and the focus task, right? So in a future study, it would be interesting to investigate like interface placed farther than the task. Second, our task was somewhat contrived because we wanted to accurately measure the time they spent in each phase. So different tasks may lead to more ecologically valid tasks results. So finally, our study also tested the single task distance, right? It was just a single task at the TV. And testing multiple distance would allow us to control for effects that are specific from the headset, for example, focal distance. So that's all I have. So thank you. I'll be happy to answer questions if there's time. You can also reach me by mail if you want to.
Okay. Thank you very much, Wallace, for your great talk. I guess we have a few minutes time for a few quick questions. I would like to remind the audience to use Slido if you have questions. So let me start with one. It seems to me you presented this on one slide, the results with the blue boxes, some lighter, some darker. And from that slide, it seemed to me that the context switching time is not, it doesn't appear to be symmetrical with respect to the field of view. Is that correct? And why would that be?
Yeah, so it depends exactly in which projection you're talking about, right? Because these are distributed through this space, right? But if we, so you're talking about the place where we placed, or about the results? Because there are two things.
It was the results.
Yeah. So if you look at the results, we see that they're actually different, right? So that was one of the findings that we had. And most curiously, when you look at the vertical displacement, right? So if you look horizontal versus vertical, we can see clearly that the lower positions are like faster than the upper ones. But if you look at just the horizontal displacement, then they're kind of symmetrical. And one of the reasons was that we wanted to distribute the screens on the left and the right side to avoid having participants just turn to one side.
Okay, thank you. I was wondering, does the cognitive effort or the cognitive load, does that have any influence on the, the design or the placement of the information?
Yeah, so thanks. That's interesting. We didn't actually measure that, but we expect that would be the case, right? So in our study, we specifically looked at just glanceable interface that are interfaces that have very low cognitive load by definition, right? So something like looking at a clock or looking at a message. So there are things that you can actually capture very fast what is going on and go back to what you're doing before. But as we increase the complexity of those interfaces, right? If it's a text or something that requires like visual search or something like that, we would expect different results. Yeah.
Okay. Thank you very much. I think in the interest of time, we have to leave it at that. I would also like to thank the audience very much for attending. This concludes the session on visual rendering. For those of you in hubs, you might want to use the break to say hello to your fellow neighbors. And that concludes the session, and I would just like to wish everybody a good further conference and stay healthy.